Okay, so we're now going to talk about some theory associated with dynamic considerations. And we've been doing problems all the semester on dynamic problems using explicit dynamics. So we've sort of, in our applications, have gone from quasi-static to dynamic and mixed. We even had quasi-static and mix of dynamic problems in different steps. And then we've sort of gone to other areas, and then we're in that domain now in our applications. And there we have thermal problems and vibrational analysis. And vibrational analysis is kind of what we're considering. It turns out that the theory used for vibrations is similar in the sense that is similar to other dynamic problems and the way we solve those solutions. So I sort of consider all of these things in one window, although there are subtopics. So vibration is a subtopic of dynamic considerations. Here on this slide I'm showing dynamic considerations on more explosive type problems. So not really vibrational type problems, but actually loading. And so this dynamic theory that we're going to walk through is applicable to problems like collisions, drop tests, explosions, and typically our problem in complexity increases. We get nonlinear responses, and also what happens is we actually, as if you look at these numbers, they actually get smaller duration. And so they're very fast events that are very complex. And there are some items listed down here that are, many of them are near and dear to my heart, my research group of what we do. So that's something to say, and then we've sort of been doing drop tests, and we've been running these methods all along. Now, for example, plastic response, durations, complex body change interactions, contact, severe deformation, so our tube crushing would fall in that domain. So we've been using the theory and the explicit dynamics. In this lecture, we're going to cover vibrational analysis, okay, as a subfield of dynamic considerations. And of course, vibrational analysis is used on most, or if not all, engineering components to understand its modal response and kind of that critical mode where we want to avoid the loading in that regime, right? To do this in the theoretical for the finite element method, what we're going to do is define a Lagrangian. Okay, and Lagrangian is just a way to write these potential energy terms, or these total energy terms. So we have L is equal to T minus pi. Okay, T is the kinetic energy and pi is the potential energy. So this pi is what we've been dealing with so far. So in our case, the kinetic energy has been 0 in our previous consideration. Now we can apply Hamilton's principle to that Lagrangian. Okay, so we come up with our terms for potential energy and kinetic energy, and here we're looking at a one-dimensional spring and mass system, and we can write our potential energy and our kinetic energy. Of course, we have 1/2 mv velocity, that's x dot squared, and what we do is if we write that L equals T minus pi, so what we do in order to consider where this is an equilibrium, so-called dynamic equilibrium, is that we try to find extrema of function L expressed in terms of generalized variables Q1, Q2, all the way to Qn. We also have Q1 dot, Q2 dot, Q dot n. So this odd looking equation here comes from Hamilton's principle essentially trying to use a variational approach to find a maximum of a function. I guess it kind of looks similar to what we looked at Galerkin method, where we have some L term, which that's basically t minus pi, and we're taking derivatives of that and we're setting equal to 0. So in general, the idea looks kind of similar. We do have an additional time term in there that we notice. So when we apply that to our system, we basically take the kinetic energy and potential energy, and we substitute it in for our L, and we come up with this system of equations, which we can then write in matrix form, and then even sort of write that more concisely in a form like this. So we have M as a mass matrix, K as a stiffness matrix, and we have accelerations and displacements. You're probably familiar with this from a vibrations class. Now, if we extend that 1D spring and mass problem to a continuum body, we consider a solid body with distributed mass. The total potential energy, well, we spent all semester learning about that the total potential energy is 1/2 Q transpose K Q minus Q transpose F. So we have strain energy and sort of external applied loads or work applied. The kinetic energy is T equals 1/2 the integral over the volume U dot transpose U dot rho dV. And in this case, we have rho as the density, mass per unit volume of the material, and U dot is a vector of velocities in the x, y, and z direction. And as we've said before, in the fine element method, we divide the body into elements, and in each element we express U in terms of the nodal displacements Q using the shape function. So we have U is equal to NQ. In dynamic analysis, the elements of Q are dependent on time, so the individual components, while N represents the spatial shape functions defined on a master element. The velocity vector is then U dot equals N times Q. We can substitute these values in. The kinetic energy in element E is given by T is equal to 1/2 integral over the volume U dot transpose U rho dV. So we substitute in our NQ dot transpose NQ dot rho dV. Remember, with this term here, we have to distribute and then flip our transpose. 1/2 VQ dot transpose N transpose it should be vectors N Q dot rho dV, and then from that we can, the Q dots don't depend on the integral over the volume, so we can pull those out, and the volume is the element in this case. We have rho N transpose N dV Q dot. Okay, and this is basically the mass ME, and it's the element mass matrix is what we call it. ME is equal to the integral over the element rho N transpose N dV. Okay, so again, this is going to be used in a similar way to stiffness, where we have to then assemble that. So the mass matrix is consistent with the shape functions chosen and is called the consistent mass matrix. It's consistent with the shape functions chosen. When we sum these over the elements, we get T is equal to the sum over elements, TE, that's equal to the sum over E, 1/2 Q transpose dot ME Q dot, and we would assemble equals to big Q, so this is basically assembly, and we get big Q transpose MQ. Global velocities and a global mass matrix. So again, the potential energy is equal to 1/2 Q transpose Q KQ minus Q transpose F. Using the Lagrangian L equals T minus phi, we obtain the equation of motion. So if you plug that into dt dl dqi dot minus partial L partial Q sub I equals 0, and you're left with MQ double dot plus KQ equals F. So that's a derivation of the equations that we want to solve. So and of course, when we're talking about vibration problems, if an engineering structure is deformed elastically and suddenly released, it tends to vibrate around its equilibrium position. The periodic motion is due to restoring the strain energy. It's called free vibration. Number of cycles per unit time is called the frequency. The maximum displacement in the equilibrium position is called the amplitude. And in the real world, the vibrations subside with time due to some damping action. In the simplest vibration model, the damping effects are neglected. The undamped free vibration model of a structure gives significant information about its dynamic behavior, and that's what we're going to consider in the application also. For free vibrations, the force is 0, okay, like as we derived in the last equation. So we then were left with MQ double dot plus KQ equals 0. For the steady state condition starting at equilibrium, we're going to set, say, Q is equal to U sine of omega t, where this U is the vector of the nodal amplitudes of vibration, and omega is the frequency. If we substitute these values into this equation, then we get KU equals omega squared MU. Alright, or let's rewrite this, KU equals lambda MU. So you probably know this problem. This is the eigenvalue problem, right? Representing a vibrating mode corresponding to an eigenvalue lambda and the square of the frequency omega, which is the square of the frequency omega. So we're basically trying to solve an eigenvalue problem for the case where we have the free undamped vibration. So that's one particular view of dynamic problems, would be these vibrational analysis problems, and we're going to look at an application on that also. In the next video, we'll discuss how to solve the explicit dynamic problem, not so much for vibration problems, but for those impact cases we mentioned in the very beginning and that we've been looking at throughout the semester. So that will be next.